Assalamu alaikum everyone. My name is Maheen. I am from Department of BS Biotechnology and I am going to present on the topic X-ray diffraction. Slides are provided by Dr. Hammad Majeed. X-rays. X-rays are the form of electromagnetic radiation similar to visible light. In 1895, Wilhelm Röntgen, professor of physics, discovered X-rays while testing whether cathode rays could pass through glass. His cathode tube was covered in heavy black paper, so he was surprised when an incandescent green light nevertheless escaped and projected onto a nearby fluorescent screen. Unlike light, however, X-rays have higher energy and can pass through most objects, including the body. Medical X-rays are used to generate images of tissues and structures inside the body. He called them X, meaning unknown rays. Wilhelm quickly found that X-rays would pass through human tissues too, rendering the bones and tissue beneath visible. Doctors in Europe and the United States were using X-rays to locate gunshots, bone fractures, kidney stones, and swallowed objects. Honors of this work poured in, including the first Nobel Prize in Physics in 1901. Medical X-rays are used to generate images of tissues and structures inside the body. If X-rays traveling through the body also pass through an X-ray detector on the other side of the patient, an image will be formed that represents the shadows formed by the objects in the body. One type of X-ray detector is photographic film, but there are many other types of detector that are used to produce digital images. The X-ray images that result from this process are called radiographs. Wilhelm Röntgen. Few scientific breakthroughs have had as immediate an impact as Wilhelm Conrad Röntgen's discovery of X-rays, a momentous event that instantly revolutionized the fields of physics and medicine. The X-ray emerged from the laboratory and into widespread use in a startlingly brief leap. Within a year Röntgen's announcement of his discovery, the application of X-rays to diagnosis and therapy was established, the part of medical profession. What is X-ray diffraction? X-ray diffraction (XRD) is a rapid analytical technique primarily used for phase identification of a crystalline material and can provide information on unit cell dimensions. The analyzed material is finely ground, homogenized, and average bulk composition is determined. X-ray diffraction or XRD is technique for analyzing the atomic or molecular structure of materials. The technique is often known as X-ray powder diffraction because the material being analyzed typically is finely ground down to a uniform state. Diffraction is when light bends slightly as it passes around the edge of an object or encounters an obstacle or aperture. The degree to which it occurs depends on relative size of wavelength compared to dimensions of the obstacle and aperture it encounters. All diffraction methods are based on generation of X-ray in the X-ray tube. These X-rays are directed at the sample and the diffracted rays are collected. A key component of all diffraction is angle between the incident and diffracted rays. Powder and single crystal diffraction vary in instrumentation beyond this. How does XRD works? X-rays are the form of electromagnetic radiation include wavelengths measurable in nanometers. A nanometer is equivalent to 1 billion of the meter. Crystals are regular array of the atoms. Whilst X-ray can be considered as waves of electromagnetic radiations, crystal atoms scatter incident X-rays, primarily through interaction with the atom's electrons. This phenomenon is known as elastic scattering. The electron is known as the scatterer. When monochromatic X-rays scatter from a substance with a structure on the scale, it causes interference. This results in a pattern of lower and higher intensity due to constructive and destructive interference according to Bragg's law we will discuss later. With the crystalline substances, the pattern creates the three-dimensional shaving of diffraction. It responds to X-ray wavelength, like the spacing of the planes in the crystal lattice. This process is known as constructive interference and is used a technique of studying crystal structures and atomic spacing. They act constructively in a few specific direction as determined by Bragg's law 2d sin theta is equal to n lambda, where d is the spacing between diffracting plates, theta is the incident angle, n is an integer, and lambda is the beam wavelength. The specific direction appears as a spot on the diffraction pattern called diffractions. Consequently, X-ray diffraction patterns result from electromagnetic waves impinging on a regular array of scatterers. X-rays are used to produce the diffraction pattern because their wavelength is often the same order of magnitude as the spacing. Crystals atoms scatter incident X-ray primarily through interaction with an atom electrons. A regular array of scatterers produce a regular array of spherical waves. In the majority of direction, these waves cancel each other out through destructive interference. How they are constructively in few specific direction. All diffraction methods start with emission of X-ray from a cathode tube or rotating target which is then focused at the sample. By collecting the diffracted X-ray, you can analyze the sample structure. This is possible because each mineral has its unique set of d-spacing. D-spacing are the distances between planes of atoms which cause diffraction peaks. There are standard references pattern of d-spacing which act as a comparison when using XRD to identify the structure of sample substances. The way that XRD reveals the atomic structure of crystal is based on the Bragg's law. What is the Bragg's law? Diffraction will only occur if the way the direction and substance interact meets to the condition of Bragg law. This requires that a beam of X-ray is directed toward a sample. The angle of the incident is equal to angle of scattering and the path length difference is equal to integer number of wavelengths. This allows for a condition maximum intensity which then enables the calculation about the details of the crystal structure concerned. Bragg's equation is n lambda is equal to 2d sin theta we discussed before. In the most of simplified forms, a generic X-ray scattering measurement is shown here. Now here we will see that a beam of X-ray is directed towards the sample and the scattered intensity is measured as a function of outgoing direction. By convention, the angle between the incoming and outgoing beam direction is called 2 theta. For the simplest possible sample consisting of sheets of charge separated by distance d, constructive interference, greater scattered intensity is observed when Bragg law is satisfied, which is n lambda is equal to 2d sin theta. Here n is integer 1, 2, 3 or so on. Lambda is the wavelength of the X-ray beam and theta is the half of scattering angle 2 theta shown above. Real materials are more complicated of course, but the general result holds that there is relationship between interparticle distances within the sample and the angles at which the scattered intensity is the highest, with larger distances d corresponding to smaller scattering angle 2 theta. What will XRD measure? XRD benefits and applications are mainly covered in this slide. X-ray diffraction can do the following: measure the average spacing between the layers of rows of atoms in the substances. This is to identify crystalline phases and orientation. Measure the average spacing between layers of rows of atoms in the substance. Determine the orientation of an individual grain or crystal, determining the structural properties such as lattice parameters, strain, grain size, epitaxy, phase composition, and preferred orientation. Measure the size, shape, and internal stress of small crystalline areas, which is in identifying the crystalline phases and orientations. And last, identify the crystal structure of an unknown substances, which is to measure the thickness of thin films and multilayers, and then determining atomic arrangements. What is the difference between the XRD and XRF? XRD identifies and measures the presence and amount of minerals, and they are specific in the sample as well as identify the phases, whereas XRF will produce an array by giving information on the chemical composition of your sample without indicating what phases they are present in your sample. X-ray fluorescence XRF and XRA diffraction XRD analyzer provide qualitative and quantitative material characterization for detection, identification, analysis, quality control, process control, regulatory compliance, and screening for metals and alloys. Mining and geology, scrap and recycling, environmental and consumer safety, education and research, and general manufacturing is also included in the XRD and XRF research. The basic difference is shown in this slide, which is mineralogy of the sample, phase identification, and XRF determine chemistry of sample, which is elemental composition. In XRD, we can have compound analysis, which, for example, contains Fe2O3 versus Fe3O4, polymorphs CaCO3, and calcite versus aragonite versus waterite. And in XRF, there is elemental analysis, which contains only Fe, iron, contains calcium, Ca. Thank you. This is all from my side. The next part will be continued from my teammate Hajra Kamran.